It must have been a year or two, maybe even 3 years ago. I was watching the Game Grumps playthrough of Katamari Damacy.
This fucking music is really bizarre.
I agree. Everything about this game is bizarre.
Never played the game, I've just watched them play the game, and I thought it was super cool because of this rolling physics, objects pick up objects, blah blah blah, it's recursive. I liked it so much that I tried to make a tutorial a while ago, also a year, 2 years, 3, I don't know. And quite frankly, it's embarrassing. Like, the accruement physics don't work, it's kind of like a half-baked solution, and for the objects that it's picking up, I used at the time what was very new. You make a model, you use stable diffusion to like project a texture onto it. I called this an air conditioner. It was rough at the time. I don't know, this is almost like a technology checkpoint. We're in the world of 3D models from an image or text. Before we do physics, let's get like a basic object. I kind of like the idea of collecting a lot of soldiers. Maybe there's like something to that, I don't know. Some kind of metaphor about the inevitability of war. Little green army men. Oh yeah, this is what I want. Let's get one of these. This guy's not happy to be picked up. I like that one, that one, that one, this one. So it's like there's a whole militia trying to guard against this. And then for the 3D generation itself, I'm going to be using a up-to-date model, specifically Tencent Hunyuan. They are sponsoring this video indeed. This happens to be one of the best models out there currently, and it's free. We like free. Go to this website, basically, which will give you a bunch of Chinese or Mandarin. I don't understand it. I assume you don't understand it, being a English viewer. We have the magic of Google. Let's make this English. All we need to do is say, do I want to use text? Do I want to use an image? Let's upload a picture. You can also do multiple images of a bunch of angles, but I only have one angle. Use the more up-to-date model. Do I need PBR? Probably no, but let's generate anyways. As this is working, we have only 17 attempts to get Katamari objects. I don't want to scour Turbo Squid for a bunch of models for a temporary project. I can also use this invite friends to get more credits, which, as Gen Alpha says, or Gen Z, is diabolical, because there would be a lot of people watching this, so I could get infinite generation. As this is working, we have a few minutes to start the rolling physics. Now, rolling physics isn't necessarily obvious how to do. If I rotate this via a driver, so the frame number over 30, or maybe the negatives, it's going to keep rolling like this, which means I can kind of put this on the ground such that it is making contact, keyframe this over time, also going on the y-axis, and there just isn't contact made 24/7. So rolling physics isn't intuitive, especially as this thing is collecting objects and they're attached to it, and the shape itself is morphing. I'm going to show you a basic trick of how to do this. It's basically a simple geonodes modifier. Geometry nodes get rid of everything. A Katamari ball is basically, or maybe let's use a icosphere. It is basically a ball like this, but with kind of protrusions, almost like these hills that make the rolling look more interesting. Sounds like a pain to model, but a beauty to model procedurally. I'm going to add some divisions here. Also going to make a second version that only has one division. What am I doing? What I'm doing is I'm saying I have a smooth circle, and I also have this sphere that all I care about is its points, right? So if I do a mesh to points right here, these points are what I care about, and these is where the protrusion will happen. Take geometry proximity to this low res one, and what that is going to look like is kind of this like soccer ball looking map. If I now set position such that we grow it outwards, so in other words, for each point, I'm going to look at the normal vector and scale in that direction, offset by a scaled version of the normal. We now have a simple setup where I can scale it up, and then finally, instead of picking a single number, I use this distance as the amount that I increase it by. And just like that, I mean, I don't really need to modify it much. That looks interesting. You can kind of up the contrast here so that there's just kind of tiny bumps going through. Maybe they're a little smooth. Now when this rolls, there will be more like visual interest. No matter how much this rolls, the key insight is that whichever point is on the bottom, so for example, this one should be contacting the ground, at any time, we need to look at the bottommost point and see how negative is it on the z-axis, or in other words, what is the z height of the bottom point. I can then take this number and shift it up. So let's just kind of rotate this a bit more. Now it's kind of like up here. I check the height and then I move it up. That is basically the essence of it. To calculate the minimum position, what I used to do is take an attribute statistic because it has this nice minimum. This isn't the fastest way to do it, because if I take the bounding box, like what is kind of inscribing or covering this, it has the same minimum z height. No matter how much I transform it, it's always going to keep that minimum z height, and that's going to be easier to calculate. Take the minimum. I only care about the z component, so I can separate x, y, z, or even better. Let's take the minimum and multiply it all by zeros, and then finally on the z, I invert it by -1. If the minimum is over here at like -2. I multiplied by -1. Now it's a value of 2 that I can move upwards. Set position of the original geometry by this offset. And just like that, it is pegged to the ground. It will now work both when it's rolling and when it is moving. So let's just do the same thing again. Hash frame over 15, hash frame over 15. These numbers should actually be dependent on each other, but we don't care right now. And look at that. It is rolling, and no matter what we add to it, no matter what disturbance, it will kind of keep doing that, as can be shown with this beautiful demo. This mess right here is going to be our ball, and then this right here is our ground snapper. It is our ground. Input a geometry, snap it to the ground, and we are good to go. Looks like this is now done, and sheesh. I mean, can we look at the original image? It's like he's proposing to somebody, but very serious. Very serious. Will you marry me? And it will not be a fun marriage. Pretty dang good. Well, the beauty of this is we need a lot of these so we can rapidly prototype. I'm going to take this model, which also has PBR maps, although I don't really care about that, and I'm going to download it. GLB is fine because it packs everything. So download that. And then let's just make another. So upload image. This time I'm not going to generate PBR because we're not going to use it anyways. Let's try to import in our first one and see what that looks like. Here's our GLB. I'm going to call it Army 1. Bring that in right here. We have our little army man, which coincidentally, I guess compared to this ball, it kind of looks to scale. I mean, it should be really tiny, maybe like 3 inches tall. Sorry for doing, I don't know if this is triggering to anybody. Apply transforms, 2.5 inches tall, which seems to be scaling this by 0.06. So set that to everything. And now, sheesh. Okay, whatever. This is just what we get. As for the model itself, it first of all comes in very detailed, which is great if you want a detailed model. It is not great if I want to simulate it compared to this. Also, it comes with materials, which in this case is quite simple. It's green. Comes with a green base color. And then it has a metallic roughness packed map, which is pretty interesting. And then finally, a normal map. That, of course, is great, but I don't need to get fancy. I just need a green material. So take this, call it the correct shade of green. These things tend to be pretty rough and pretty shiny. So I'm going to make it rougher, but at the same time, I'm also going to say make it really, really shiny. And then for the bump mapping, I want it to kind of look like plastic. So I'm just going to make kind of these micro distortions. Noise texture. What am I going to use? I'm going to use object coordinates. Now we have a nicely uniform noise that we can send through a bump node, connect that there, and come on, Eevee. Okay, we have our bump. Make that way smaller and way less strong. And that already made it look like plastic in my eyes. How are we doing on our other model? It is done. It's not showing, so I'm just going to refresh. Go to my assets, which is like everything I generated. Tried it out yesterday on the Mona Lisa. And yeah, boy, that's what I'm talking about. Download the GLB, start up a new one, 16 to go. What have we not done? We haven't done the military rocket launcher guy. I'm excited. I can't get off my seat. And I wonder, can we run concurrent processes? I've just accepted the Chinese. I'm not going to do English. As that is working, can we do concurrent things? I thought we had one more. Is it like a bad image format? It's this one right here. AVIF. Nothing that GIMP can't handle. Boom, boom, boom. Army converted. Boom. Okay, let's try that again. There we go. Generate that bad boy. And yeah, looks like concurrency parallelization works. There we go. That's what I'm talking about. Download. I'll wait for the other one to finish and then I will report back. I love I can just browse Twitter as this is going. I don't know if you've seen this guy, by the way. I don't know how he has the time for this, but every single day he makes like this matchstick animation. Okaza Kitomo Hero. He kind of has phases. So here's like his like wiggly phase where he makes colors. You can see kind of same thing over here. I mean, look at this. Just pure creativity. Here's one I really like. Like, bruh, how do you make this every single day and also make it, like, look so seamless? Okay, let's go way back, see what he was doing, like, a month ago or something. So I know we were generating 3D models, but, like, should I have been, like, a matchstick influencer this whole time? I kind of get the sense that this guy, like, has, like, an art grant or something, or maybe just money isn't an issue, and he could just do whatever he wants. Okay, anyways, how are we doing here? We're doing great is what we're doing. Here we have our temporary army of green men. And for now, let's kind of pivot them so that they're on the bottom. You can use the same process I just showed you, or we can just kind of center these bad boys, take all of them, snap them to the ground. Guess I have to do one at a time. If you have modifiers, by the way, on multiple objects, you can control A, visual geometry to mesh, and it will basically apply all modifiers. And there you go. I mean, the pivot point should now be correct. Only other thing I want to do is because this is going to be a heavy simulation, especially once we have like 100 of these, is I'm going to take these soldiers, which again, right now have a ton of geometry. And first of all, in edit mode, I'm going to merge by distance. This got rid of a lot of vertices. face. And additionally, I'm going to apply a decimation. So instead of 500,000 faces, if I go down to like 0.1, remember these are going to be really tiny. Now we're down to 50,000. Kind of looks the same. Let's go even lower. Looks like at about 0.02, we lose a bit of the face detail, but honestly, these are tiny. This is fine with me. Control L to link what? Link modifiers. So now these will all inherit that same thing. Control A, visual geometry to mesh. And now we are indeed cooking. This seems much more manageable. I'm not getting any lag or anything. All of these army men, I'm going to put in a collection called objects because we might add more later. And let's just start like randomly scattering these around. So this can be here. Duplicate these a bunch of times. I'm going to start off simple and just have a ball roll along the x-axis. To kind of randomize these a bit more, you can select everything, randomize transform, which will do nothing until you start playing with the location a little. Modify the Z rotation so that they're not all facing the same way, and even a bit of scale variation. So some of them are like taller than others. Finally, you can do a random select, which I'm going to turn into deselect. So I'm just kind of picking some of these over here. For whichever ones are selected here, delete them. This will kind of break the pattern a little. Here we have our lineup of army men. I'm sorry for what I'm about to do. Our sphere now, in comparison, is way too big. We're going to take our ball, which again has this radius for both the smooth version and the kind of faceted version. Connect these so that they're sharing the same radius, and let's just kind of bring that down. Our proximity kind of equally scales down. If it's 10 times smaller, you expect the distance to the nearest point to also be 10 times smaller. Scale this, like divide by the same number. Just gonna scale this a little. Now, what I want you to remember is we've kind of generalized all of this. We said we have a ball, we snap it to the ground, and in fact, we don't care about what happens in between. It will always snap to the ground. So if I rotate, it will snap. If I move it, it will of course remain snapped. I want to have this roll and move in this direction. And then to kind of accumulate these army men, we have to ask ourselves, how do we know if a army man has touched the ball? And in that case, what do we do to it? You can see right here, we'd say it made a contact. And the way we know that is there's been a intersection or a collision. You can either kind of evaluate this by seeing like which geometry is inside the other, but much more simply, point over here and a point over here. If there exists a pair of points that are within some distance, like they're half a centimeter, 0.1 centimeters away, and that's for any point. We can check this one, this one, all of them. If any pair of vertices kind of satisfies that condition, we can call it connected. It means that this is now part of the ball's geometry and they rotate together. These kind of move and they rotate together. We've gotten close to this army man, which is touching the overall geometry because there's 2 points that are close enough, and then this joins, which is joined to this. Sounds like a simulation zone issue. We're going to start off with the ball. We're going to make sure it's on the ground on every single frame and output that. That calculation's happening again and again, but nothing is visually happening. Before we snap it to the ground, let's say that two things happen. One, we're going to move it a little on the x-axis. So now if I play this, it just kind of moves down. Second of all, it's going to rotate. And you might be thinking, CG Matter, why are you not using the transform geometry? The reason I'm not doing this is you can see it gets wonky. What's happening here is as the geometry is over here, it's still going to rotate, not like this, but it's going to be centered at the origin. So the pivot point of the rotation is much bigger. Instead, what we do is we set positions, and then for rotating the actual points, I want to calculate the center of mass or center of volume of this object and say rotate about that. Well, just like before, what I can do is I can use a bounding box. If I take the minimum and the maximum and average them, in other words, saying where is the middle of the box, I can mix A, I can mix B. This is the center of mass. In fact, what I can do is I can kind of separate this over here such that we do the bounding box first, and I'm going to do an offset for the position, and the rotation I can do actually here. Vector, rotate. We have to say what do we rotate, about what center, about what axis, and by how much? Well, let's take it step by step. We are rotating the position. The center of rotation is what we just calculated over here. So this is the center of the bounding box. The axis, if we're traveling along the x-axis, is we want it to orbit about the y-axis. 0, 1, 0. And then the angle we're going to figure out, but you can see it's actually rotating nicely. And if I play this, it's working now. One issue you might notice is I'm picking these numbers pretty arbitrarily. In fact, if I set the location to be way slower, now the rotation's going too fast and they're not dependent on each other, whereas they should be. I'm going to say I want the speed of this, how much it's moving. I want this to be fixed. Okay, so I can literally combine X, Y, Z and give this a very specific number. We'll call this 0.02. I then want this angle to be dependent on the speed. So if it goes really slow, the angle should be low, whereas if it goes really fast, the angle should be high. The rotation is going to be dependent on the circumference of this, kind of like the bounding circumference. If this is contacting the ground over here, here and I'm moving by like a centimeter to the right, this should roll such that the new point of contact is a centimeter along this circle. So how much I move it is exactly how much I rotate it so that the pivot point always is correct. They move in proportion to each other. Well, first of all, I need the circumference of this shape, which is going to be dynamic, but it will always be 2 pi r. 2 pi is just a number, and the radius is basically kind of a measure of how big is this at any point. How do we calculate this? Again, we use the bounding box. I'm going to say that the radius, I'm going to calculate it by looking at kind of the difference on the z and then the difference on the y, and I'm going to say, give me whichever one of these is the biggest. So in this case, it's probably going to be the x. It seems like wider than it is tall. Take that and divide it by 2, and then this section is going to be the radius. So no matter how much it rotates, we can always find which axis is the biggest. It's an approximation, but it will do. I'm going to take the maximum and then subtract the minimum. It's going to give us the vector from one corner to the other. I then want to say, look at the x, y, and z separation and tell me which one of these is the biggest. That is exactly the same as taking the maximum of the x and y and then the maximum of that and the z. This calculation right here is our diameter, which is twice as big. So let's actually divide by 2. This is going to be our radius. And then remember, we multiply by 2 pi to get our circumference. And I know we're dividing by 2, multiplying by 2 times pi, there's cancellation, but for now we're going to leave it as is for readability. We now need to use this information to calculate what should this angle be. Well, first of all, we're moving by this quantity. That is going to be some proportion of the circumference. That is going to be some percent of this total circle. To figure that out, I'm going to take 1 and divide it by the other. So you can think of this as saying this is the ratio of the circumference I traveled. And then finally, I need to take this and translate it into how much rotation to do that. Now, because we can use radians, 1 radian is exactly the same as the distance along this of 1 radian. It's a very special quantity, which is convenient for us because then we don't have to do any fancy conversions. We're going to take this, we're going to use it as the angle, but I think we just got to make sure that it is in radians. Either that or the opposite. Okay, that seems a little off to me. What did I not include here? I think what I'm missing is I don't want to multiply by pi. Let's see, I'm going to get rid of this, and then I think that's correct. Okay, so what's the rationale? Saying we traveled by this amount, we'll call it x. Because again, radians has that special property where it's kind of proportional exactly. It is equal to the arc length around the thing. All I need is the ratio between the radius. The radius is exactly 1 radian. That's why they have a similar name, radius, radian. I need to find the proportion between that and how fast we're moving. If you've lost the plot, so have I. So let's take all of this nonsense and just kind of hide it. Take all of this noise, Control G. Just like that, we have a node group for our movement. So if I have 0.015, it's like that. If I make it twice as slow, then also the rotation will slow down. And then if I do 0.03, it should speed up the rotation. Amazing. The last thing we need to do, because this is dynamic and we'll recalculate the radius at all times, is we need to say these army men should join the ball under certain conditions. To do this, I'm just going to bring in our army men collection. Make sure to set this to relative. I believe you can hide the objects. And I want to do that proximity step saying, are there a pair of points that are close enough to each other for each of these? Right now, this comes in as a single instance. I'm going to separate these so that we have 25 instances, because we should have 25 of these. And before we look at the points, which involves realizing these instances, I want to keep a tab over which instance did it originally belong to. So I'm going to store named attribute, a instance attribute, instance index, the integer of the index, so that when I realize this now, if I go to the vertices, you can see all the beginning ones have a instance index of 0, and then as you scroll down, it's like 14 up to 24, because indexing starts at 0. This I'm going to feed into my simulation zone. At the top, we have our Katamari, and on the bottom, let's call them loose objects, things that have not been connected yet. We need to check which ones remain loose and which ones don't. Now, because all of these are independent from each other, each army men, the calculation should be separate. I'm going to use the forbidden, the lovely, for each zone. And we're going to say for each something, do this check. It wouldn't really make sense to separate by point or edge or face. We need each of these to be on their own. That's exactly what the instances were, but I realized that what am I doing? The magic is going to be in the split to instances node. This will let us convert back and forth, essentially. I'm going to take our loose objects, and I'm going going to split into instances. But how do we know which belongs where? Like, how do we know that this army man is separate from this one? Well, that is exactly what this instance index thing was for. So I'm going to look at the instance index, separate into instances, and then for each element, I can look at the instance. I want to say, take this, so each army man individually, give me its geometry. So again, we're going from instances back and forth, and then I want to check the proximity to the ball. That is literally as simple as taking geometry proximity to this ball that we moved and then set to the ground. I'm going to look for the nearest face is fine, and I want to check, is it close enough? Is the distance, let's say, less than like 0.01 or something? But we need to do this for every single point, right? This point right here, we'll check, is it close enough? This point right here, we'll check. All I care about is, does at least one of these points satisfy? I can take our army man, I can do an attribute statistic of this distance. Let's kind of hide that here. And I'm going to look at the minimum, the smallest distance. How close is it really? If the minimum is less than, let's say, 0.01, then I'm going to call that a collision, which we can handle outside of this for each element zone. Store a named attribute of this army man. It will be a Boolean called hit. So has it collided? And then for the ones that satisfy this condition, we're going to say it indeed hit. So in other words, once we output this here, this for each zone just does a calculation to see which one has hit independently. Based on that, I can say which parts are still loose and which parts now belong to the Katamari. We're going to take this output, which represents all of the inputs joined together, and I want to now separate geometry based on what is and isn't a hit. Tell me what is a hit, connect that there. For the ones that are a hit, just join them with the original Katamari. Join this together, and then anything that doesn't hit now is a loose part, which will work recursively because then we, again, take the loose parts, split them into instances, do this operation over and over. So I'm just going to look at the Katamari, not anything else. If I play this, yeah, you can see they're kind of joining together and it's working that way. The inverse of this, the loose parts, are exactly the army men that have not been picked up. Join these together to visualize both and look at that moment by moment, frame by frame update. It's working. Why is it so dang slow? Well, if I turn on the timing, so you can see here it's taking 1/4 of a second per frame. You can do that by toggling this. The slowest step is this for each, and then inside of this for each, we're kind of doing this geometry proximity. If I take 14 milliseconds multiplied by however many there are, that's an issue. It turns out that looking at which point is substantially faster than the face. So now we're getting something way closer to real time just by changing that. Notice that this one survived. Why did it survive? Well, the army man next to it connected, which then made it taller, right? So if I look at it this way, amazing. Amazing. The game developer headed people of you. You're thinking, this can be so much faster. Like, what do you mean you're checking every single point pair for like a collision check? I know, there's a faster way. You could kind of approximate it saying, instead of looking at this army man, just kind of look at the convex hull or even the bounding box. Because if it touches the convex hull, most likely touch the army man, and the convex hull is far fewer vertices, right? So if I look at this ball, I use a convex hull node, you can see we went from 10,000 vertices to just 1,000 vertices. But for now, I'm not too concerned about it. I just want like super accurate collision. I guess as a final note, remember, all of this is just looking inside of this collection of objects, which means I can add something at any time. So let's say it goes through a bunch of army men, and then let's have it go through something a bit bigger. Let's get back to Tencent. What do I want? Maybe this time I can use like a text prompt. So maybe, what's slightly bigger than a green army man? A green army general? Like keys, maybe? Or I guess a key is kind of the same size. Like a matchbox, maybe? I have no idea why I'm drawing a blank. This is like the simplest thing. I'm saying what is smaller than my fist. I mean, if I'm saying smaller than my fist, why not? Let's just do a fist. I think it's probably going to give me a man. Let's just do realistic fist. Let's do a general, not cartoony thing. Generate now. Oh, gives us options. I did not know that. The results are starting to come in, and we do have a bunch of different kinds of fists. I think for this one, I'll remove the background. Okay, let's wait for it to texture. Okie dokie, what do we got? We have options to choose from. Some of them look different than others. I do like this one. This one seems pretty simple and like what I want. Let's download that. I like this except for the background, but we can remove that, download that. Did you know you can bring in multiple GLBs? I don't even know if that's true. Let's try it. It is true. I knew it all along. Merge by distance, apply the decimation, go to wireframe mode so you can select through things, or you can actually just enable X-ray. Select everything you want. Control I to delete what you don't. And can we just click L? L lets lets you select linked islands. Get rid of the background, boolean, difference, cube, apply. Love it. And then for this one, I'm just going to use it as is. Comparatively, how big is a fist? Kind of depends if it's a baby hand or not, right? I feel like this one looks slightly bigger. Put a fist there, maybe some more army men. This was such a better idea in my head. I'm going to make sure these fists are on the ground, hit that a little, and apply. So just add it to your collection of things, and theory, it should now just work. Let's see if it indeed collects the fists. So army man 1, 2, 3. By the way, this is why you might want to use bounding boxes so it doesn't waste calculation there. And oh yeah. Oh yeah. It's everything I ever dreamed. So there you go. My Katamari Damacy tutorial with AI-generated 3D models, which is perfect for something that is about collecting objects of all kinds of types. I know this one ran long. Hour 15 minutes to record on my end. I would love it if I could get this under 25 minutes. We'll see. Again, you can check out Tencent Hunyuan. There's a link in the description. If you want to, you get 20 free uses per day. So pretty cool. Goodbye.